Hello, my name is Saloni and I'm the team leader. On behalf of my team, I'm excited to present our work on toxic comment classification, which focuses on developing a model for toxic comment to improve online communication. Let me introduce my team members who have contributed to this project. Ankita Chavan, who have worked on dataset collection and data preprocessing. Sonal Solanki, who was in charge of building Flask application and project report. Kanishka Pawar, who focused on model development. With that, let's dive right into the objective of our project. As we all know, the internet is a powerful platform for expression and connection, but it also comes with challenges. Among these, toxic comments such as hate speech, abusive language, and personal attacks pose a significant problem. They not only disturb meaningful interactions, but can also lead to mental health issues, discourage participation, and foster toxic environments online. This project focuses on addressing this challenge by developing a system to detect and filter toxic comments effectively. Our goal is to create an automated solution that identifies harmful language while allowing constructive communication to thrive.
Let's move on to the objectives of our project. Myself, Ankita Chavan. The objectives of our project are threefold. First, develop a robust model. Create a reliable system to accurately detect and classify toxic comments. Second, improve user experience. Enhance online interactions by filtering harmful content, ensuring a safer and more enjoyable environment. Third, promote healthier discussions, foster constructive and inclusive conversations by reducing toxic behavior on digital platforms. These objectives aim to make online spaces safer and more respectful for all users. For this project, we used a dataset from Kaggle, which contains three key files. First, trend.csv. This file includes label data for training the model, with comments categorized as toxic, severe toxic, obscene, threat, insult, and identity hate. Second, test.csv. This file contains unlabeled data used to evaluate the model's performance. Third, sample submission.csv, a sample format for submitting predictions demonstrating the expected output structure.
Now, let's discuss about exploratory data analysis. Myself, Kanishka Pawar. For the exploratory data analysis, we focused on three key aspects. First, class distribution. We analyzed the frequency of each label to understand the imbalance in toxic and non-toxic comments. Second, comment length distribution. This helped us observe the variation in comment length and set appropriate padding dens for preprocessing. The last one would be word clouds. We generated word clouds for toxic and non-toxic comments, highlighting the most frequently used words in each category.
Our pre-processing pipeline involved the following steps. First, tokenization, converting text into sequences of tokens for easier processing by the model. Second, text cleaning, removing unnecessary characters, punctuation, and stop words to standardize the input. Third, padding, ensuring all sequences have the same length by adding padding tokens where needed. Fourth, handling imbalanced data, applying techniques like oversampling or class weights to address class imbalance. Fifth, splitting the data, dividing the data set into training and validation sets to evaluate model performance effectively. These steps ensured clean, balanced, and well-structured input for our model.
For this project, we evaluated four deep learning models. First, ANN, Artificial Neural Network, a basic model for identifying patterns in the data. Second, CNN, Convolutional Neural Network, leveraged for capturing spatial relationship in text embeddings. Third, LSTM, long short-term memory, designed to capture long-term dependencies in sequential text data. Fourth, bidirectional LSTM, enhanced LSTM by considering both past and future context for better understanding. These models were chosen to explore a range of architectures suitable for text classification tasks. Our project utilized four deep learning architectures tailored for text classification. First, ANN, artificial neural network. This model includes an embedding layer, flattening the data, followed by several dense layers for classification. Second, CNN, convolutional neural network. We used an embedding layer, convolutional layers, global max pooling, and dense layers to capture local patterns in the text. Third, LSTM, long short-term memory, incorporating an embedding layer and LSTM layers to capture sequential dependencies in the data. Fourth, bidirectional LSTM. This architecture extends LSTM by processing text in both forward and backward directions, improving context understanding.
Myself, Sona Solanki. Let me walk you through the key steps of our model training process. The very first one is data preparation. We begin by pre-processing and tokenizing the text data. The data is then split into training, validation, and test sets. Second is model compilation. The model uses the Adern optimizer with binary cross entropy loss for multi-level classification. Accuracy is used as the primary evaluation metrics during training. Third is training configuration. Each model is trained for 5 epochs with a batch size of 64. Validation is performed after every epoch to monitor progress. Last is evaluation. Finally, we evaluate each model using metrics like precision, recall, and F1 scores. This helps us choose the best performing model for balanced multi-label classification. Let's discuss the results and our final model selection. Overall accuracy. The BI-LSTM model achieved a high accuracy of 97.87%, showcasing its ability to learn patterns in the data effectively. Precision. Precision was relatively low at 14%, indicating the presence of false positives, particularly in less frequent toxicity categories. Recall. Recall was strong at 85%, showing that the model performed well in identifying toxic comments, especially for the more common classes. F1 score. The F1 score is 24%, reflecting the need to balance precision and recall for better overall performance. After comparing several models, including ANN, CNN, LSTM, and BI-LSTM, we've selected the BI-LSTM model as it provided the most balanced and robust performance across multiple matrices. In conclusion, the BI-LSTM model stands out as the best performing model, and it will be used for toxic comment classification in our project. Now let's move on the demonstration of our model in action. In this video, we will show you how the trained model classifies comments as toxic or non-toxic. First, we will input sample comments into the model. You will see how the model processes the text and provides predictions. We will also showcase the model's confidence in its classification for each comment.
The success of toxic comment classification project highlights the effectiveness of deep learning in addressing the challenge of online toxicity. By utilizing the BI-LSTM model, we achieved a high level of accuracy and consistency in classifying various toxic behaviors, ensuring that the model can effectively distinguish between different types of harmful content. This work not only provides a robust solution for content moderation, but also contributes to the development of safer online spaces by aiding social media platforms in identifying and managing toxic interactions. With this strong performance, the model can play a key role in promoting healthier digital environments and enhancing user experience on social media platforms.